So welcome to another QuTech360. These seminars that we run every month, I guess. Today we have Alberto Bordin. Alberto is a last year PhD candidate in the group of Leo Kouwenhoven here at QuTech Delft. And today he will tell us all about Kitaev chains and how they are trying to engineer these here. And so the floor is yours, and I wish you a nice.
Thank you, Giordano, for the nice introduction, and thank you everyone for coming to this talk. Indeed, today I'm going to present the work I've been doing for the last 4 years of my PhD. And first of all, I want to thank all the people that are with me in this big effort in trying to engineer Kitaev chains under the supervision of the professors Leo Kouwenhoven and Srijit Goswami. So indeed, thanks to all the people here, and let's see what this big team was able to produce in the last years. If you're here at the QuTech360 Seminar, probably you are familiar with the concept of qubits, and in particular with the fact that they are very fragile because they couple to the environment very easily. So this line of research that I'm going to discuss today, it's indeed, wait a second, I don't see the clock. In case I'm going too long, please give me 5 minutes. So indeed, this line of research aims to combine these fragile qubits to something that is robust against perturbations by definition, which is the concept of topology. So can we actually combine these two concepts and find a way to engineer, to store the quantum information in a topologically protected way? Well, we don't know if it's feasible. It hasn't been realized yet. But 20 years ago, Alexei Kitaev proposed a model in order to make this in real practice. And this model consists of a chain of n sites, and this is indeed called the Kitaev chain. And it has, every site has a chemical potential mu, a hopping term T, and then neighboring sites also have a pairing term delta. So these are the ingredients that we need, and this is what I'm going to discuss during this presentation, how we can actually get all these ingredients in practice. And what's interesting here is that if in a specific parameter region, it's possible to have Majorana bound states at the two ends of the chain. And what are these states? Well, we can see them as simply a change of basis with respect to the electron and hole creation and annihilation operators. So far, nothing but a mathematical trick decompose the fermions in their real and imaginary parts. And with this trick, we can see that, for example, gamma 1 is C plus C dagger, which means that gamma 1 is gamma 1 dagger, which means that every mode of this Majoranas is actually its own antiparticle. And it also means that if they have any energy, this energy must be zero. So we're actually after zero energy modes. And another property that we want to keep in mind is that a number operators, dagger C, if you write the C's in terms of the gamma operators, then you get gamma 1, gamma 2. So this means that indeed one fermion is 2 Majoranas, and that's also another thing to keep in mind. Okay, so far just the trivial change of basis. And we can have here, for example, a 5-site chain, and we can see it as decomposed into 10 Majoranas side by side. But as long as they are coupled side by side, nothing fancy happens. But it's more interesting if we can find a way to couple them in this way. So 2 with 3, 4 with 5, and so on, which leaves 2 uncoupled Majoranas at the two ends of the chain. And since 2 Majoranas is 1 fermion, this will be a fancy way of storing one single fermion half here and half here in a non-local fashion, indeed protected topologically by this bulk. So this is what we want. And another interesting property is that they are neither fermions nor bosons, but anyons. Indeed, if you exchange them, you get a non-trivial phase that can be used to have single qubit gates. Not all of them, to be honest, just the Clifford ones. So we will need something else. But at least these ones can be done in principle in a protected fashion. All right. So again, what we want is this, and our shopping list is trying to buy a mu term, a t term, a delta term, but also we need to remind that we need to leave the spin degeneracy. Indeed, here there is no summation over the spin degree of freedom. So we need to get rid of the spin multiplicity. And the easiest way to do it is put in a magnetic field different from 0 and split the two spins. And then we want to be able to tune the chain in order to have indeed edge modes. Let's go. Let's try to realize this piece by piece. Starting with the mu term, this can be realized using quantum dots. And in our case, we start from a semiconducting nanowire, which we deposit on top of a keyboard of bottom gates. We can connect those gates to room temperature electronics and to voltage sources. We can add a source and a drain and connect them as well. And we can see this as simply, we can define barriers on the two sides using these gates here, which decouple the central parts from the source and the drain, and see this as a quantum dot weakly coupled to the neighboring contacts, which is controlled by a gate just underneath it. And here we can see a measurement where this gate is indeed varied. And what we measure is the current when the electronic levels hit the resonance. And we can see here that, we can see here that indeed they appear in pairs, just like just like the orbitals in an atom. We can also have two dot systems this way. In this case, we will have a map instead of just a trace, but the idea is the same. Here we can imagine to, for example, take a vertical line cut, horizontal line cut, and this is basically taking a line cut. You have a trace like this. This is old data from over 10 years ago. This is from one measurement of ours. So, I mean, this is very well known. And what's nice here in this two-side, and you can see in this two-side map, is that you can also, if you count the electrons here, and you count them in this way, if you take into account the two quantum dots here and here, then you can see that there is a little bit of an avoided crossing here. So the 0-1 region is actually coupled to the 1-0 region, which means that this system with two quantum dots already creates a hopping term of this type. It has it already. And this is very typical. This is data from 10 years old. So it seems indeed that quantum dots are a very nice starting point. But what about the delta? Well, that's harder, and that can't be realized using just bare semiconductors. So the idea, also proposed around 10 years ago, was to add superconductors to the mix in between separated quantum dots. And indeed, this was also realized recently with the difference that instead of having a bare superconductor, we have a hybrid semiconducting superconducting region. This was first fabricated and measured by Guan and others. And this is a sketch from that paper. And indeed, this is able to couple electrons from neighboring quantum dots via this hybrid. And these quantum dots these electrons in neighboring quantum dots are coupled via a process called CAR, which we can see as either Cooper pair splitting or forming. And indeed, what it does is creates an electron here, or it annihilates both into a Cooper pair in the superconductor. So indeed, we can have this as well, and you can find all the details here. At the same time, in the same system, we can also have a tunneling term in between the quantum dots. This is nothing really special. It's like the T I was showing before. But since now it happens through the hybrid, we call it elastic co-tunneling, just to remind that it's a second order process. But it's the same principle. So great. We have, in principle, all these elements. But the question is that it might appear not so trivial, is can they exist at the same time? Because actually, when you put a field, magnetic field that is different from zero, then we encounter a spin problem. And the fact is that the normal tunneling preserves the spin, while the cross-under reflection or Cooper pair splitting couples spins of opposite species. And so it seems here that there is no way to combine these two processes if we select a specific spin for every quantum dot. Fortunately, in our system, I lost the presentation. Okay. Fortunately, in our system, we have spin orbit coupling that rotates the spin as the electrons move. Indeed, the spin orbit coupling couples the momentum with the spin degree of freedom. So as long as the electron travels, it can rotate. And this gives a finite spin flipping probability that can make sure that there is a finite probability of having elastic co-tunneling and cross-under reflection that are compatible. And here I'm showing a measurement where we measure a current that is proportional to this spin flipping elastic co-tunneling. And the current is in blue here. And we are measuring here as a function of the external magnetic field and its direction. So we vary the external field in all directions and measure indeed how much spin flipping elastic co-tunneling we have. And we see that for the full globe, the full globe is basically all blue. So there is always current, there is always elastic co-tunneling, apart from these two spots here, which correspond to a single direction. And this is very much compatible to this model of spin orbit coupling. Indeed, you can see the spin orbit coupling as an effective magnetic field. And if it happens that the external magnetic field and the spin orbit effective field are parallel, then the spin cannot precess. So indeed, we interpret this direction here as the direction of the spin orbit coupling. Okay, quick summary so that we can go on with the great foundation. Indeed, we could have the mu term using quantum dots that have control on the energies. We could have the T and the delta term using a hybrid that can mediate elastic co-tunneling and cross-under reflection. We could set the field at a value different from zero and still having compatible elastic co-tunneling and cross-under reflection. And now the question is, can we tune the system to actually have Majoranas? And fortunately, we found out, oh yes, before I want to stress indeed why specifically for two-side chains, this tunability is so important. And someone please bring me a little bit of water because I'm very dry. Thank you very much. And indeed, let me write down the Hamiltonian of a two-side chain. But since we don't want to spend too much time on maths, let's just look at this diagram, and I will try to convince you that you can just look at these lines which represent these Hamiltonian terms. And the point, thank you very much. The point here is that indeed, as I was showing in the first slide, if you write down the gamma 1 times gamma 2, so these two, then you end up having a C dagger C if you change the basis. And this is basically the mu term here. So coupling these two Majoranas is setting a mu that is different from 0. And in the same way, you can find out that by writing down the products gamma 2, gamma 3, you get T plus delta, and writing down gamma 1, gamma 4, you get T minus delta. So indeed, by just looking at this, we see this as the mu coupling terms, this positive diagonal as the T plus delta terms, and this negative diagonal as the T minus delta term. So if we go to this specific condition with the mu1 equal to mu2 equal to 0 and T equal to delta, then these mu lines and these anti-diagonal lines will disappear, and we will have two isolated Majorana states here and here at the two ends. And these are called poor man's Majoranas because indeed you need to tune to this specific sweet spot in order to have them. But if you're able to do so, then still you have two separated Majoranas, one per dot, and they have 0 overlap if the tuning is precise. Okay. We were lucky enough to find out that in our hybrid, it is possible to tune this ECT and CAR amplitude that corresponds to the T and delta. Indeed, here we are measuring the amplitudes of CAR and ECT as a function of the hybrid gate underneath the hybrid. And we see heavy modulation here, here, and here. And in particular, if we correlate this heaviest modulation with the presence of this subgap states in the spectroscopy of a bare hybrid, then indeed we can also study the details and find out that these processes, CAR and ECT, are actually mediated by these subgap states that are called Andreev bound states, ABSs. And all the details are described here. But I'm not going to talk about the details too much. I only want to stress out that indeed, using this trick, using the presence of these ABSs and changing the gates underneath, we can modulate these two processes. And what we can have is having a region here in orange where the ECT is dominant and the region in blue where the cross-under reflection is dominant. Indeed, in this ECT dominant region, we can also measure the charge stability diagram that I was showing in one of the first slides, like this one, and find out and avoid a crossing of this type that is coupling the 1,0 with the 0,1 region. And if we go to the CAR dominant region, then we can find the opposite type of body crossing, which is something new that is not usually seen in quantum dots. And that's indeed coming from superconducting. And this is coupling the 0,0 and 1,1 regions. And what's good is that in our system, we can actually transition from one type of coupling to the other by simply varying a single gate underneath the hybrid. This was first demonstrated in this paper by Tom and others. And in particular, at this central point here, which we call the poor man's Majorana sweet spot, we have, instead of having an avoided crossing, we have a cross. And at the center of the cross, the spectrum looks like this. And you can see here that there is a blue line and an orange line because the spectrum is taken on the left quantum dot and on the right quantum dot, and they nearly overlap, which is indeed compatible with having a poor man's Majorana mode here in orange on the right and in blue on the left at the same time. Okay. This was also reproduced in multiple other devices. And here there is another paper showing also increased protection and gap here. And this data is indeed from this paper from Francesco, who's in the audience, and many others. And just borrowing data from here, I want to also show that indeed, besides requiring this careful tuning, these Majoranas already have some protection. And if you go along one of this green dotted line, for example, you can see that the zero energy mode stays stable over the full range. And we can again see in the diagram by simply having one coupling term between these two that starts to appear as soon as we move along this line. But this Majorana stays uncoupled, stays untouched. And since Majoranas come in pairs, so 2 Majoranas is equal to 1 electron, here, since we have an odd number of Majoranas, is simply like having 1. So also in this case, the Majoranas are uncoupled and the zero mode stays. However, if both quantum dots are tuned together, then the Majoranas are coupled via this Z. And indeed, we can see that the zero mode splits and as it's separated by this energy here. What's nice is that it's splitted quadratically, which means that also from perturbations of both chemical potentials of the first quantum dot and the second quantum dot, there is still a little bit of protection. It's quadratic. It can be worse. Indeed, can be worse because this is what happens for the coupling terms T and delta. Here I'm showing further data from the same work, where indeed following a profile where there is a dip here in the T term and the peak in the delta term, pretty much like the one I was showing before. And here there is the spectrum. We can see that there are 2 sweet spots, one here in black, and there is the one here, and 2 here. And in these 2 sweet spots, there is indeed a linear splitting of the zero mode that is not stable against perturbations of this hybrid gate. And this can be seen indeed as coupling directly this term and this term via the T minus delta coupling. Right. So this is very much calling for scaling up the system to 3 sides. And that's what I can't click anymore. I can. Yes. Okay. Right. So indeed, this calls for scaling up to 3 sides. Because indeed, if we couple these 2, then the edge Majoranas are coupled. While if we couple these 2, then this will remain uncoupled. And indeed, we can see this on the simulation of the spectrum. Here we have this linear splitting I was showing before. And here in a 3-side scenario, we have a persistent mode in theory, if only one chemical potential is perturbed. So I went to the clean room to fabricate this device, and this is a sketch of how it looks like. There is still a semiconducting nanowires, 2 aluminum strips, and on the edges 2 normal contacts. And everything is deposited on top of a keyboard of bottom gates in pink. Here is where we can define the quantum dots. And here is an energy diagram showing the first contact, the second, the third, and the fourth, and how they are also connected to separate voltage meters, voltage sources, and current meters. And again, what we want is to realize this Hamiltonian. So we want a mu term, and we can get it having quantum dots. We want a T and delta term, and we could indeed demonstrate that we have them. And here I'm not going through all the details. You can find them here. But indeed, we could see, and you can see them from this current spots here on the 4 terminals, 1, 2, 3, and 4. We could identify all the possible combination of processes that move one electron from the first quantum dot all the way to the second. For example, either via a double elastic cotandaling event, or via a double cross-under reflection, where, by the way, the first one is Cooper pair forming and the second one is Cooper pair splitting. Or we can also have hybrid combinations of the two, so CAR plus ECT and ECT plus CAR. And we were also able to identify those. So great. It seems that we have all the elements also in a three-side chain. It seems that the system is pretty much scalable. And we'll see at the end why this is important. But of course, we also need to remind that we don't need to just have all the terms, but we also need to be able to tune them. And so we set a magnetic field different from 0 in order to split the spin degeneracy. And what we want is to balance the cross-under reflection and the elastic contact. And we do it in this three-side device, but to do it side by side, we first put the third dot of resonance so that the chain is effectively two sides long. And we do the same game, balancing the car dominant region with the ECT dominant region until we find the cross. And here at the center, indeed, we have this zero bias peak corresponding to a Pullman's Majorana mode. And if we detune following this diagonal, we see again the characteristic quadratic dispersion of Pullman's Majorana modes if both chemical potentials are detuned. And in the same device, we were able to play this game on the left two dots and also on the right two dots, where I want to stress that the gate settings of this middle dot here and here for these two scenarios are exactly the same. So these two configurations are actually compatible. And this is already a nice result because it shows that our tuning procedure in order to get Pullman's Majorana modes, it's quite robust and reproducible. We can have it multiple times on the same device in different parts, and also with the constraint of having the same settings in the middle quantum dots. And then what we want to do is to put all the elements together and see if indeed having three sides increases the protection. So we can indeed take a look again at this quadratic splitting and compare it with the situation when we put the third dot on resonance. And here it is. Well, first of all, the first thing we noticed is that indeed the spectrum changes. It's not the same. And this is already quite remarkable because I want to stress that these two measurements are done in the same exact gate and parameter configuration. So all the 11 gates are tuned to the same value, apart from one gate, that is the plunger gate controlling this third dot. So these two measurements are identical. The only difference is the middle gate of the third dot, and look at how much the spectrum is affected. And this already means that the system is a joint correlated system. It works together. And also, the way it is changed is very nice, because instead of having a peak splitting here, we have a zero bias peak that stays for a longer region. And indeed, we tried this also choosing different pairs of quantum dots. And it doesn't matter which pair you pick. It doesn't matter if you detune them in the same direction or in the opposite direction. You always have a persistent zero bias peak if only two dots are detuned. If you want to split the zero bias peak, you need to tune all of them. And that's what we did as well. And also in this case, we found out that the degree of splitting is a little bit less than this one. And you can see that in these line cuts here. So in these values here, in blue, you have this. Then in red, there is the zero bias peak here. And in green, there is this splitting here that is a little bit less than the blue one. And indeed, if you detune all dots, this splitting is supposed to be quadratic, and this splitting is supposed to be cubic. So indeed, we have a little bit of protection, added protection. But this is not the biggest deal. What's most important is taking a look at the protection against the coupling terms T and delta. Indeed, this is what we were measuring on the Pullman's Majorana system I was showing before. And this is a reproduction of the same result in the two quantum dots, the first two quantum dots of our three-side chain. Here there is also a gate jump, so this sweet spot marked by the pink arrow, you are seeing it twice, but it's the same thing. And what's interesting is that if we play the same trick of placing the last dot on resonance, then we get a stable zero bias peak over the full range. And this is quite remarkable because indeed it says that if before moving a hybrid gate, so changing either T or delta, could couple the two edge modes, now it can't do it anymore by itself. Actually, there is no single parameter that can couple these two edge Majoranas because this coupling here is not allowed. There is this system doesn't support next to nearest neighbor hopping. So this drawing is not allowed. And if you want to couple this Majorana with this Majorana, then you need to draw at least two pieces, like here. And this indeed means that there is a qualitative difference that is what is adding this protection. Okay, to conclude, I want to quickly discuss some slides on what is the perspective, what are the next steps in this quest for topology in condensate matter. The first very important step is to add a loop to the system, because it's true that in this system that I was showing before, we can have and see Majoranas, but what we can't control is the superconducting phase between the two superconductors. And because these are separately grounded in our system, and this means that even a small voltage noise in the two grounds translates into a phase uncertainty in between the two superconductors. And this is very bad, especially if you want to make a qubit. So the first necessary step is to connect the two into a loop. And this is an ongoing effort. And this is one of the first devices that was fabricated, but I failed at a different step. So this is indeed work in progress. And luckily, there is very promising data already coming from our two-dimensional electron gases friends. And here is the device, a device that they fabricated some time ago, where here you can believe that there is a loop closing. Here we can see also a zoom in, and it's an analogous system. What is very nice is that this Pullman's Majoranas or Kitaev systems are not platform specific, but they were reproduced very soon from our two-deck friends, and in two sites, and now also in three sites. With the added freedom here that they can not only add a loop very easily, but also add probes to the left, middle, and right. So in particularly also to the middle dot. And this way, measure the conductance on the left, middle, and right. In particular, they can measure this conductance as a function of the magnetic field out of plane that induces a flux in the loop I was showing here, in the loop here. And indeed here you can see a periodic evolution of the spectrum, which matches very well the prediction for a change in the phase. So indeed, we believe that the phase is very well controlled by having a loop and putting a flux on it. Okay. Finally, the next step is at some point, hopefully soon, is to try to make a qubit. And this is how a qubit would look like using three-side chains, for example. You will need a three-side chain here, another three-side chain here, because you need two pairs, one pair, so two Kitaev chains in order to have a single qubit. And you should also connect them with a global loop. And this will define one qubit. I think it's quite funny that this resembles quite well a device from Lieben's group having the same number of dots and having 6 qubits instead of just 1. So what's the point of attempting this? Is there any point? Well, of course, the path is still long, but what is in the side of the Kitaev chain approach is the scaling. And this is shown in this slide here. If we plot the coherence times as a function of the number of sites, then we see that with 3 sites, we can get something. This is a simulation based on the values that we measured in our experiment. So this is not just poured out of the head, but based on experimental data, although it's just a simulation and extrapolation. And having 3 sites, we can expect to have a qubit coherence time on the order of microseconds, so on the order of the spin qubits one. If we go to 5 sites, then it's possible to reach 1 millisecond, so similar to the best transmodes. And if one could go beyond, one can also think of reaching the seconds and what they can have in neutral atoms. Of course, there are also other limits. So it's not just the noise that you have on the gates that is limiting your lifetime and coherence times. There is also, for example, the quasi-particle poisoning, that for now, preliminary data from Francesco and Nick shows that it's on the order of milliseconds. But hopefully this can also be improved in the future with better screening, so one can dream of more. So quick summary to conclude the presentation. Indeed, we were able to realize all the elements of a Kitaev chain Hamiltonian in both 2-side chains and 3-side chains. We could also balance the ECT and Carr amplitude in 2 sides and also in 3 sides pairwise. And finally, we could also show that having 3 sides increases the protection of Majorana modes, and this gives a very promising scaling for future qubits. But to conclude, I just want to stare one more time at these slides, because I want to stress that this quest is not just about an engineering challenge, a technological challenge, but I think it's also about physics. And I think personally that this slide is very beautiful, because it shows that here indeed on the left, there is a zero bias peak. Here on the right, there is a zero bias peak. And here on the center, there is a gap, which is a first experimental realization of the beginning of what is very famously known in topology as the bulk edge correspondence. So that the fact the number of modes that you have on the edges of a topological system corresponds to the topological class that you can calculate in the bulk. That is gaps. And seeing the beginning of this in a 3-side chain measured by our Schroeder Franks, I think it's very beautiful. And indeed shows that this system can be used in order to engineer topology in condensate matter. With this, I thank you for the attention. And if you have any questions, I'm very happy.